Alright, what's up, what's up, what's up? This is going to be episode 2 on the ASM video series of going from noob to veteran ASM coder. In the previous episode, it was just a brief introduction, went over what stuff you need before you begin this journey, along with 3 little threads that you need to follow so you can get Dolphin Emulator installed. You can learn how to apply cheat codes in Dolphin and also install the Dolphin memory engine. Alright, so in today's episode, we're going to go over 2 threads, Glossary and Simplified cheat code intro/tutorial. The Simplified cheat code intro is extremely important. It is probably the most important thread out of all the threads in this gigantic index of going from noob to ASM coder. Okay, because if there's stuff here that you don't understand or stuff you're not willing to learn, then there's going to be plenty of things in the future that you're just not going to be able to comprehend. Alright, let me get a sip of water. Alright, first things first, the glossary thread. Now with this particular thread, you don't need to read the whole thing, and you actually don't even need to skim it. Just use this as a reference thread for times when I use specific terms or vocabulary that you don't understand or comprehend. So if I use a certain term like Broadway or breakpoint or null, some weird term that you may have not heard before, go to the glossary thread, look up the definition. Chances are it's going to be in this thread. If not, just post a question either on the glossary thread or on the video, on this the comments on this video. So that's there just for your convenience. You don't need to read the entire thing. Just use it as a reference page. So now we got that out of the way. Let's go over arguably the most important thread of the entire series, the Simplified Beginner's Cheat Code Intro/Tutorial. I'm going to be using various examples in this video. Keep in mind these are all going to be fake and made up code examples, just an FYI. Alright, so what do cheat codes do exactly? You know, and like how do they affect the game and whatnot? Well, first, cheat codes are applied in the game by what is called a code handler. You guys probably heard of this before. It's called the Gecko code handler. Very famous, made a long time ago. The one that's used in Dolphin is a modified version of the original, so it can work on Dolphins because, you know, Dolphin's just an emulation. For this series, we're really just going to focus on Dolphin emulator, just working on the emulator. We're never really going to include the actual use on the console because things on the console compared to Dolphin can vary wildly. So, cheat codes, their purpose, essentially, is to modify permanently or temporarily portions of the game's memory. By modifying portions or certain areas of the game memory, we can make the game do certain actions that we want it to do, right? So that's all cheat codes do. The Gecko code handler in Dolphin reads whatever cheat code you have in the cheat manager and modifies memory accordingly. The technical term for memory is random access memory, but when you're a coder, you usually just go say RAM, or more often you just go say memory. Okay? Now, with mkwe.com, the main gist of our site is that we're the first ever website to have a centralized, organized database of every public cheat code for MKWe ever released. So let's just look up any random cheat code. Doesn't really matter what it is. We'll just look up anti-item spy. Right off the bat, excuse me, let me get more sip of water. Right off the bat, you're going to notice there's 4 different versions for most cheat codes. This is because when the developers at MKWe, they released 4 different versions of MKWe. You have an American version, a European version, Japanese version, and a Korean version. And each version is coded, when they made these versions, they're all coded a little differently, so therefore memory by default is going to vary a teeny bit per version, if you will. But we don't call these versions, we call it region. So we have 4 different regions at MKW, essentially. Now we're not talking about regions in actual gameplay. We're just talking about disk regions, okay? Just an FYI if people think I'm talking about regions on Wi-Fi, which I am not. So we got 4 different regions, if you will. NTSCU, which is American game. PAL, which is European game. NTSCJ, which is Japanese game. And NTSCK for Korean game. Okay? So as you can see, this is a simple code. You can see the values right here. You might have to zoom in to see this, but the values right on this particular cheat code vary slightly for all different 4 regions, okay? Because of what I explained about earlier. I also, in this simplified cheat code thread, I supplied the game IDs for each version. RMCE, American MKW, P for European, RMCJ for Japan, and K for Korea. Okay, so just so you know that, there's obviously exceptions to this rule. You can have a region-free code, or in the incomplete/outdated subforum, we may not have all 4 versions yet, just due to particular circumstances. Okay, so what I talked about earlier, the purpose of a code is to modify memory, whether it be temporary or permanent. So basically, there's 2 main sections of memory. As you can, I'm going to highlight right here. Now, right off the bat, you're going to see these FF values, like FFFFF. If you don't know what these digits, these numbers or characters stand for, when we talk about memory, we view it in compiled form, and it's represented in compiled hexadecimal bytecode is what it's called. So all values in memory are shown in hexadecimal. So if you don't know what hex is, you can find it on Google within minutes. Any tutorial will suffice. Pick whatever website looks like the best tutorial for you. Doesn't matter. Take about half an hour or so to learn hexadecimal. Once you learn it, come back and continue this video. So we can split memory into 3 different groups: Mem80, Mem81, Mem90. It's pretty self-explanatory why they're named that way, but Mem80 is any. Now, before I continue further, when I use the term memory address, that means a particular spot in the memory range. We usually just call it, as coders, we just call it address or memory address. So Mem80 means any memory address that begins with the digits 80. Doesn't really matter what the other 6 digits are. All memory addresses are 8 digits in length, just a FYI. So the first 2 digits in Mem80 is always 80. All right. Mem81 starts with 81. Mem90 starts with 90. Easy to know. Or excuse me, Mem90 means anything that starts in just a digit 9, not 90. I'll have to fix that little typo right here in this thread. Glad I caught that. But just an FYI, so we're going to, Mem80 starts in 80, Mem81, 81, and Mem90 means any address that starts with just a digit 9. Okay, so anyway, what is Mem80? Mem80 is called static memory, which static meaning doesn't alter, doesn't get changed. The instructions that the game has, which the Wii CPU, which we call Broadway, that Broadway executes, those instructions reside in Mem80. Now, we call it static, not changing, because no matter how many times you boot the game, no matter how many times you change races, or how much time elapses in the game, or how many times you go off Wi-Fi, those instructions don't change addresses in memory. So, for example, if you find a unique instruction at a specific memory address, it will always be at that memory address when you boot the game. Granted, keep in mind though that the location of this particular instruction that we're talking about will vary its memory address depending on which region of game you're working with. Okay, does that make sense? So, static memory never changes. They hold the instructions that the Wii CPU will execute so the game can function. Now, Mem81 and Mem90, they're called dynamic memory, which means they can change like all the time or every so often. Usually in this area of memory, we'll have various integer and floating point values are stored here. So essentially, it's like a hierarchy system. Mem80 is at the top, and it controls what goes on in Mem81 and Mem90. Does that make sense? Instructions get executed one at a time in Mem80. and these instructions may need to create values, read values, load values, or store them, and they use mem81 and 90 for this purpose. Alright? Now, obviously, there's exceptions to every rule. High regions, high areas of mem80, such as a memory address starting with the digits 80E or like 80F, a lot of times they're used as dynamic memory. So when I'm talking about anything in general throughout this whole ASM video series, there's going to be times where I'm just generally speaking, there'll be little exceptions to the rule, just an FYI. So let's look at screenshot what memory even looks like. So this is memory. Now this is static memory. And what you're viewing here is now to the left, right here. Now so I can highlight stuff, let's bring up Dolphin Memory Engine I have booted up on Dolphin. Okay, so the stuff on the left are address values, right? And to the right are sort of like column values. At the top, are column values, and to the right is like text, ASCII conversion stuff you don't need to be concerned about for now. All the stuff in this big epicenter, that's all compiled hex byte code of various instructions that get executed by Broadway. Alright? So, go back to the tutorial that you understand that. There's a specific rule. Every instruction's memory address must end in 0, 4, 8, or C, and every instruction is always 8 digits in length. Never shorter, never greater. So, with all that being said, as mentioned before, every compile instruction is 8 digits. Now, we usually don't, as coders, we don't refer to digits, or we don't refer to values as digits. We like to use things what's called bytes, half words, and words. Now, when I select something in this Dolphin Memory Engine, you'll notice right at the bat that first, everything is organized in like digit pairs of digits. 2 digits, a pair of digits is a byte. So most programs like Dolphin Memory Engine and various hex editors will pair this up automatically for you. So it's easier, it makes it a little bit readable, even though everything we're viewing is just compiled instructions that we can't really read it anyway. But it makes it a little bit easier nonetheless. So this 7C value, this hex value I'm viewing now that I have highlighted, this is a byte. 2 digits is a byte. Now, as mentioned before, an entire instruction is 4 bytes, but we wouldn't say 4 bytes. We would say a word. So a word is 4 bytes, which is the same as 8 digits. So if we start at the very top left, and we're looking at a word, it would include the 7C, the 08, the 03, and the A6. That entire thing is a word. Alright? Now we can go a little lower than a word, which is a half word. Self-explanatory, half of a word. It's 2 bytes, or 4 digits. Now, and then we just have 2 digits, which as mentioned before is a byte. A word is also known as 32-bit. I'm not going to go into binary for now, as that can be confusing, but just know a word equals 4 bytes, which is the same as 32 bits. Half of that is a half word, which is 2 bytes, which is 16 bits. And a standard byte is 8 bits. So you could be using the term byte, half word, and word a lot when you're coding. Okay, so let's say we wanted to view a compiled instruction at a particular address. Let's say, let me get my text editor. Yeah, this should be big enough to view. We have this memory address. Obviously, we know it's static memory because the first 2 digits, or the first byte of this value, is 80. So this is a static memory address. And another rule I want to point out is that, as mentioned before, every instruction is a word in length, and every instruction's memory address ends in 0, 4, 8, or C. As you can see, this ends in 4. So if I was to say, point to me, or navigate to me on the Dolphin Memory Engine, the memory address, the instruction, at memory address 80516.074, this is how you would do it. You start on the left-hand side right here where it says address, and you go down to 80516.074. 070, excuse me. So you're right here. Then you just go to the right 4 times. 1, 2, 3, 4. That right there is the exact spot of memory address 80516.074. As mentioned before, every instruction is a word in length. That means 4 bytes. We start with 4 bytes. 38A00000. So, the instruction at memory address 80516.074 is 38A00000. Get a sip of water and give you a chance to digest that. Okay. So now let's go a little bit more less basic. Now, if I was to say, show me the half word at this memory address, the one we're still talking about, the same one. Remember, half words are 4 digits. They're 2 bytes in length, right? They're half of a word. So going back to our Dolphin memory engine, that would include just the 38 and the A0. Nothing else. Just that. And if I was going to say the byte, what is the byte at memory address 80516.074? It would just be 38. Does that make sense? You could be using a lot of this terminology forever once you learn ASM coding. Okay, so now we got that out of the way. You understand how to navigate in memory. You know what a memory address is. And you know about words, 32-bit, half words, 16-bit, and bytes, 8-bit. Let's go over some basic code formats that the Gecko code handler uses. Okay. So now we have 32-bit RAM write. Let me type an example of what a 32-bit RAM write would look like. Okay, so whenever you see a single line of compiled code like this, like a cheat code like this is known as a 32-bit RAM write. First, let's start with this byte value right here, the 04. First of all, that designates static memory. So, to change this value, you can change this value to the memory address that the code is manipulating or modifying. You just take the 04, change it to 80516.074. So we know this code is manipulating the 32-bit value at this memory address because it's a 32-bit RAM write code. So we know it's modifying the word value at this memory address. Now this value to the right, what is this? Well, this is the value that it's going to write to in memory. So regardless of what is in memory by default, this compiled this compiled word in hex is going to replace whatever was in memory beforehand. The word is going to replace the word at 80516.074. So if you ever see a 6 with a row with a bunch of zeros after it and a word value, that's referred to as a NOP. A lot of newbie coders or people who don't really know what they're doing will take this value and apply it to different memory addresses randomly and such. You'll see it all over the place. It does have an actual purpose for real coding, but quite a bit of times when you see it, it's usually in a newbie code. That's just kind of just there to like try to cancel out an instruction to make a certain action in a game happen. So for most 32-bit RAM write code, you're going to see this. It's called a NOP. So when a coder says NOP this address, it would be talking about applying this compiled value to a particular memory address. Or if someone says like, oh, NOP this, NOP that, that code is a NOP. This is what they're referring to. Now, sometimes you won't see a NOP. Sometimes you'll see like various compiled instructions, like something like this. This wouldn't be a NOP, but this is still replacing a compiled instruction with a different compiled instruction. All right, but let's just go back to the NOP. Now, if we have a code like this, we know it's affecting this memory address. What would actually happen? So, going back to Dolphin Memory Engine, once the Gecko code handler loads up your cheats and interprets them and applies them, what's going to happen is at address 80516.074, which is starting right here, is going to replace whatever word value is here, these 4 bytes, with the NOP. Just like that. That is what would actually happen in the game to memory. And the cheat code is applied. We will revert back to the old value. And let's say we take that. Let's say you see a code like this. Now what is this code? This is a 16-bit RAM write code, or you can call it a half-word RAM write. The 02 designates static memory, mem80, so we can change it to its memory address. Now, if you've been paying attention, you would know that half-words can never exceed 4 digits in length. They can never exceed 2 bytes, or 16-bit. So this is why whenever you see a 16-bit code, RAM write code, there will always be 4 zeros at the beginning. Alright? And just an FYI, sometimes coders will use the term null for a byte of 0. So this would be 2 bytes of null. That will always be there. And this is the half-word value, this FFFF, that's going to be written to RAM at this memory address. Okay? Does that make sense? So if we had this code in our cheat manager, it would be applied by the code handler like this. Navigate down, go to the right, just like that. Nothing else would be modified. So let's say there is something other than zeros right here. If you can see, that's stuff I'm clicking in blue. Let's say it was just, those are just the values of 1111. They would not be affected because we're only writing a half word. Okay, so 32-bit RAM writes are designated by 04 for the first byte, 16 bits 02. Now let's go into 8 bits, which is 00. Take that out. We'll go ahead and just put this here. Give me a second. We'll put our default compiled instruction value back in. So if you see this is an 8-bit RAM write. Obviously 8 bits meaning a byte, which is 2 digits. This is why these 6 zeros always have to be there, because a byte can't be longer than 2 digits. So this is the byte value. We take the 00, change it to 80 for static memory. So this byte value of 1C is going to be written at memory address 80516.074. Alright, go back to Dolphin Memory Engine. So here, it would just write the value 1C. That's it. Nothing else will be affected. Make sense? Give you some time to digest that. Take a sip of water. Okay, so we've gone over 32-bit RAM write, 16-bit, 8-bit. We talked about what a NOP is. Now let's talk about controller lines. This is going to be a little confusing. Whenever you see codes that have this line, usually they'll have it twice. It's the purpose to activate and or deactivate a code at will. Now, remember I told you that memory by default is different per every region? So we have this P value, which you usually won't see in cheat code threads. Now this P value is 3 for Korea and 4 for all other versions. Alright, for Japan, PAL, and USA. The X values is a half-word value representing a memory address. Essentially, for example, let's say we have 384XXXX. It's actually translating it into the static memory address. Essentially, the game, in certain portions of static memory, will have a certain value depending on what controller you're using. Right? So these XXX values will vary depending on what controller you have, right? Now the Z values are button values, and the Y values is an equation to decide whether or not the code creator wants the player to have the ability to press other buttons while pressing his activator or deactivator for the code to work. In the next video or a future video, I will explain how to fill in these XYZ values. But just understand that the X's stand for the controller address, the Z values is the button values, and the Y values is the equation to whether or not a person is allowed to hold other buttons while pressing the activator or deactivator. So that is the controller line essentially. Alright, and another thing too is in this thread, the simplified cheat code tut, I provide a link to a thread listing all the known MKW X and Z values, alright, because they were discovered a long time ago, so you don't have to do the work of trying to find them yourself. And another thread, teaching you how to fill in XYZ values, which I'll put in a separate video so you can learn how to do that. So just know when you see this 2834 or 2833 line, those are for manual activation, deactivation of codes via the controller. Alright, so now let's go over what a compiled ASM code looks like. This is a compiled ASM code. Alright, now I just want to go over what ASM code looks like so you get an idea when you see an ASM code that you know it's an ASM code. First off, this C2 byte at the beginning, this designates an insert ASM code, so we know it's an ASM code. Just like all the other compiled Gecko code formats we've been working with, just take the value, change it to 80, and plug in the rest of the numbers, and you get the memory address that this code is manipulating. As you noticed, all of these have been static memory addresses because this is where the instructions that control all the other memory reside at. So this is why 99.9% of codes, when you see their memory address that they're referring to, chances are it's going to be static memory. Now you can see right off the bat, you see these word values right here? Those are compiled instructions, and you know that this is a NOP. But just know that these are compiled instructions. This word of zeros is for the Gecko code handler. I'm not going to go into it, but all ASM codes end in a word of zeros. It's just a Gecko standard. But just keep in mind that these three word values are compiled instructions. Now, this byte right here, whenever you see a C2 code, on the top right word, these 6 digits are always 0, right? Those 3 bytes. Now this 4th byte right here designates how many lines below is the compiled length of code. So it says 2, we got 1, 2. 2 rows of a compiled code. Obviously you got to remember this value is in hex, so you might see something like 1E or 0A or 5C. Alright, so that's all that means. Just want to go over that so you know it's an ASM code. Okay? Halfway terminators and final terminators. Copy that in. I might have to backspace some stuff. We'll just keep it halfway and final. Taking another sip of water, guys. I'm a little parched. Running low on water. Okay, so now, as you can see, there's some stuff we've already gone over. For example, look. We got 2 controller lines. And when you see 2 controller lines in a code, usually 99% of the time, the top is the code or the controller line that activates the code, aka in this scenario we'll apply our 32-bit RAM write of a NOP, and the second line is the deactivator controller line. And the deactivator means this value would be the default compiled instruction value, and it rewrites it back to RAM, so it restores the default instruction and essentially turns the code off. In most cases, that will happen. Keep in mind, this is a fake code. I have no idea what the values are at this address. As mentioned before, we're working with just made-up examples just for ease of use on the fly. So now let's go over these half-word and final terminators. Essentially, what these controller lines do is they create an if statement for the Gecko code handler. And what these halfway and final terminators do, they're like end ifs, essentially. So if this, and if that. That's why they're kind of there. Or that's actually why they're actually there, for that particular reason. But just know when you see this in this E0 line with E all zeros, that always goes below, like for example, after your code. So for example, this is after our RAM write, and it always goes before your second controller line. It's needed. It's required for the Gecko format. And whenever you finish it off, this is the final terminator. This E with the rest of the zeros, 8,000, 8,000. Oh, I actually dragged that. So that final terminator is needed so the Gecko code handler knows that that particular code is done with and it's time to read the next code whenever these if statements are created. But if you just have a bunch of 32-bit RAM writes, obviously you don't need halfway and final terminators. Now let's go with the off and on switch. And keep in mind, this is an off-on switch, not an on-off switch. Okay, so as you can see, this is a little different. We don't have a second controller line anymore. However, we still have two 32-bit RAM writes. Alright, so what this code does is, it applies whatever is underneath the CC value first, it applies this value. Now this, remember we talked about, for most cases, let's just pretend this would be the default compiled value or the default compiled instruction value at this particular spot in memory. We know this would be the memory address. Take the 04, change it to 80, plug in the rest of the values. So it would apply this value to memory first, and then once you press your button for whatever you've set your button to be your activator, it would then apply the NOP at that same memory address. Press the button again, it goes back to applying this value, and over and over and over every time you press. And obviously we need the final terminator because we have a controller line. Make sense? Okay. String write. This one's going to be a little odd. Let's just take a look at an example. And we're going to plug in a memory address we were using earlier so I can show you what actually happens in memory. So first things first, the 06, the first byte, represents a string write. Just take that, convert it to 80, plug in the rest of the values. That's the static memory address we'll be modifying. But it's going to modify more than just that word at that address because we're dealing with a string write. Now as you can see, we have 6 compiled instructions. Now this top right byte, keep in mind this right here, these 6 zeros are always 0. The byte here is going to designate how many bytes in length the string write is. And remember, this 18 is in hex. It's not actually 18, it's more or whatever. So if you count all these bytes, counting in hex, and you get to the last one, 14, we end up with the value of 18 in hex. So what would happen if we applied this code in memory? Well, let's go back, bring this to the top, go back to Dolphin memory. Now we start here. This is our starting point, highlighted in blue. We got to write the first compiled instruction, aka the NOP. Then we go to the next one. Go to the next one. And make sure I didn't miss one. Sorry guys. I'm a little new to this video creating stuff, narrating and whatnot. Make sure I get the right values in at least. Sorry if I mess up typing these. But you get the idea. It writes a string of values starting at the memory address that's designated next to the 06 byte at the top left here. So that's what it does. You can see we got 1, 2, 3, 4, 5, 6. 6 total compiled instructions written in memory. And if you look in the compiled code, 1, 2, 3, 4, 5, 6. Now, you might have something odd like this scenario right here. Let's say we have this. Now, if you've been paying attention, you notice in Dolphin Memory Engine, or when you view memory, all memory in each row has 4 words. So everything's like word aligned, if you will. Technically not the right term, but just for newbie's sake, just understand that you see there's 4 words per every row. This is why I explained earlier that well, I don't know if I think I probably forgot to mention this. Hopefully I didn't. But every instruction, its address, the value of its address will always end in 0, 4, 8, or C, right? So this compiled instruction 7C0803A6. Well, it's at this memory address 80516000. Because starting here, and you go to one word total, it ends there. So this 38210010, that's at memory address 80516004. Go to this 4E800020, that's the compiled word instruction at 80516008. Go one more over, 00C. So this is why for like all 32-bit RAM writes, for most other RAM writes, and for insert ASM codes, the one with the C2 byte, all of their addressing is gonna, like this, is gonna end in a 0, 4, 8, or C. So sorry I forgot to mention that earlier, but that's actually pretty important. So going back to our string write, let's say we had this little issue. It goes to the bytes, but it ends right here. It doesn't end at the very end. So when this happens, and you see this, as long as the code creator is writing their string write correctly, the leftovers will always be 0. So if this was like 13, this must be 0. Now the reason is, let me put that back. Now let's just put AA for now. What's going to happen is, go back to Dolphin memory. When we wrote our string write, navigate here, first instruction, second, third, fourth, fifth, sixth. Let's say we apply this code now. What's going to happen is, it's going to apply the string write, but it's going to stop here at AA, which is AA right here. Does that make sense? So whatever values are right next to right after the AA that's left of this like word right here, they're not going to be affected. So just know in the future, way down the road, if you ever do write string writes and they're not like aligned perfectly for the amount of words, they always end in a bunch of zeros, the leftover zeros, and whatever's in memory at that particular spot, as if the zeros are there, nothing's going to be written there. Okay, so that might be a little confusing, but chances are you're not really ever going to use string writes. It's very rare. And let's go over one more format. Let me just copy paste this example. So let's say you have the rare chance of modifying dynamic memory, like if you found a portion of dynamic memory that acted as static memory. So what this code would do is, first you need this for-to line. This creates an if statement, which is why it ends in a final terminator, which you need. And let's say what this will do is, first off, this memory, this mem90 address is being affected. So let's say you want to write the NOP. We'll backtrack a bit. Let's say you want to write a NOP at this mem90 address, right? Which is very rare because usually, like I said, mem90 is dynamic. You write this for-to line. This is called set base address. And then you write this, the beginning of mem90, all right, which is 9 then all zeros. After that, you just make a standard 32-bit code. And then that way the Gecko code handler knows by this for-to line up here that it's going to do a RAM write, but at mem90, not mem80. And thus it will write this NOP at this mem90 address. And then, as I mentioned before, finish it off with the final terminator. All right, and that's pretty much it. In the thread, I provide 3 more examples. One with like a 8-bit RAM write activating and deactivating it. Another one with a 16-bit RAM write with an off-on switch, and also an active code that activates and deactivates, but it activates an ASM code and deactivates via a RAM write. So this is just going to give you a general idea of what compiled codes look like, and when you see various compiled codes, you know generally what their purpose is. And we've gone over memory, all 3 portions of memory, compiled instructions. Every compiled instruction is 4 bytes in length. It's a word, and every instruction's address must end in 0, 4, 8, or C. All right. We've gone over words, half words, and bytes, and I think that is everything. I'm getting a little parched here. So in the next episode, We're going to talk about filling in XYZ values. I might include the activator and deactivators, importing codes all in one video. I think I'll do that, and that's really about it, guys. Sorry if I'm not really the best at teaching and narrating, so I might have a little been all over the place, but hopefully that helps you understand and helps you visualize what words, half bytes, and bytes are, and how to navigate in memory properly. Alright, thanks for watching.